Good morning, ladies and gentlemen. My name is Pedro Vellasco, and I come from the State University of Rio de Janeiro. And today I will present a paper entitled An Experimental Assessment of Hot-Rolled Carbon and Stainless Steel Equal Lag Angles Under Compression. This is part of a PhD student thesis, Mr. Sirqueira, and in this paper we also have some colleagues from the State University of Rio de Janeiro that collaborated in this project. My presentation will be divided in 6 main topics. First, introduction, followed by the structural design of angles under compression. Then I'll present you the formulations of the Eurocode related to this design, and this is followed by the experimental program description and some of its results. And finally, I'll brief some of the conclusions. The use of stainless steel profiles has increased in the present years and has been boosted in structures due to their numerous structural benefits and aesthetic features. The stainless steel mechanical properties are similar to carbon steel, but stainless steel has nonlinear characteristics that makes imperative to have design recommendations that are not equal to the carbon steel one. We have to modify them, especially when we look at instability ultimate limit states. The investigation that I am going to present you today involves experiments performed on hot-rolled carbon and stainless steel columns made by equal lag angles, and these experiments were made subjecting these cross-sections to compression. The experiments that I'm going to show you today were made on 500 and 1000 millimeter length columns, and the failures that were related to these ultimate limit states involve the flexural-torsional buckling. In this section, I will present some of the interesting investigations that have been performed in the structural design of angles in compression. A very good example of that is the test that was performed by Reynolds involving 33 welded duplex stainless steel angles with 3 different cross sections. The angles had free and fixed rotation supports in the minor and major inertia axis, and the results proved to be in agreement with the American design standard that uses a flexural buckling curve. On the other hand, the flexural-torsional buckling ultimate limit state was not accessed by the limited amount of experiments that were performed. Menezes has performed experiments in 13 austenitic rod-rolled angle tests with heights varying from 250 to 1500 millimeters, and the failures were divided in 2 modes. For lengths less than equal to 750 millimeter, the flexural-torsional buckling control, while the other tests had their failures associated to flexural buckling or a minor flexural buckle. The normalized slenderness stress values less than 0.65 when we assess what's in the Eurocode report 1.4 proved to be conservative, while for values more than 0.65 they proved to be unsafe. On the other hand, the continuous strength method proved to be unsafe for all sections. We could see that the majority of the investigation involving stainless steel compression response was centered on cold-form profiles that considered strain hardening and the local and global buckling mode interaction. But we could see that there were very limited studies involving the flexural-torsional buckling of stainless section, as it was reported by Ashram et al. And Becky and Rasmussen. The Eurocode 3 design formulations that will be assessed in these papers involve the part 1.4 that is for stainless steel and the part 1.1 that is for carbon steel. All these standards they involve the use of buckling curves, especially for stainless open section common, and in this section we could also see the presence of the flexural-torsional buckling. The hot rolled equal leg angle sections in process in both design standards involve the flexural-torsional resistance with these equations. In this equation, the term KFT is the flexural-torsional buckling reduction factor defined by this equation with the buckling coefficient phi evaluating with this formula. We have a summary of the 8 tests that were performed in columns with 500 and 1000 millimeter heights that involved sections of a leg of 60 and a thickness of 5 millimeters in both stainless and carbon steel. Here we have the two main failure modes associated to these sections. The first one involves a minor axis flexural buckling that was not related to any of the tests that we are going to show you today, but we had in some of the tests that involved higher columns, and the one that is the flexural-torsional buckling that occurred in all the tests that I'm going to present to you and involve the major axis flexural buckling together with a rotation of the section. The experimental program involved a series of measures that had to be taken to achieve the desired results. But the profile we had to be cut precisely perpendicular to the cross section, and the base plate had to be welded to ensure its squareness and verticality. The base plate and the test system plate centroids were forced to coincide, and the test top and bottom plates were fully fixed to inhibit rotation, only enabling a vertical displacement to achieve the desired buckling length coefficient of 0.5. Here we have a typical instrumentation that were used in the test that uses LVDTs all over the height of the angles, sections, and linear strain gauges that we use to monitor the strains and stresses when the load was applied. In this graph, we can see a typical load versus axial displacement curves for the 500 millimeter columns, in which we could see the difference between the stainless and the carbon steel responses. Similar response was achieved when we look at the 1000 millimeter columns, in which we can see the stainless and the carbon steel difference were. It's notable that a significant difference in structural response can be observed for both heights, and it explicitly tackles the difference between the carbon and the stainless steel columns. In this table, we could see a comparison of the results of the experiments and the Eurocode predictions for the 64 by 64 by 4.8 equal leg angle columns, where all the predictions underestimated from 52 up to 66% of the test failure loads, confirming the code conservatives. That is natural due to the lack of tests that we have in this section. These are the typical deformed shape for the carbon and stainless steel sections with 500 millimeter height that involves the rotation and the major axis flexural buckling, characterized by the flexural-torsional buckling. In conclusion, we present you some tests involving the flexural-torsional buckling of hot rolled equal leg angle sectional columns, using ASTM A36 carbon and 304 austenitic stainless steels with heights of 500 and 1000 millimeters. The test program involved the structural response of these columns made by angle sections with different normalized. A 30% ultimate load difference in terms of structural response was observed for both investigation heights when we assess carbon and stainless steel columns, and the failure modes for all tests was the flexural-torsional buckling. The results were used to assess the accuracy of the design methods present in Eurocode 3 parts 1.4 and 1.10, and in all the predictions it was clear that the column ultimate load capacity was underestimated, with values ranging up to 66%, confirming the natural code conservative that is naturally due to the lack of experience that we still have. Lastly, I would like to acknowledge the financial support granted by the Brazilian national and state science support agencies for the present investigation made by CNPq, CAPES, and FAPERJ. Last but not least, I'd like to present some of the features that we made during the tests. Here we have the 500 millimeter height columns, and we can see that as the load applies, we can see a very substantial deformation of the column that involves the rotation of the section at the center of the column and the flexural buckling in the major axis. Although we have not reported in the paper, we have also made some tests with greater heights, like this column with the 2000 millimeter, in which we had a failure associated with the other ultimate limit state that control the design of this section, which is the minor axis flexural buckling that we could see around the middle of the column as the load progresses and we have its deformed shape. And with this slide, I finalize my presentation, and I'll be available to answer some of your questions later on the section. Thank you very much.